2 videos ago, we stated Newton's first and second laws of motion. And last video, I had a brief rant about the difference between inertial and gravitational mass. And now, with all of that aside, now is time to go to Newton's third law of motion. And Newton had a hard time stating it in a way that even his colleagues were happy about at the time. In the first few editions of the Principia, he actually went with a short sentence, which was very un-Newton-like. He simply said, to every action there is always opposed an equal reaction. However, he found that created a lot of confusion with his colleagues, and so in most of the editions, he replaced that final period with a semicolon and went, or the mutual action of two bodies upon each other are always equal and directed to contrary parts. Okay, so what does this all mean? And it is quite a mouthful. So let's try to break it down. First thing, like we had intuited, is that all physical interactions are mutual. So there's always two players. In fact, there's always exactly two players. Never just one player, never three players, always two players. And both players in an interaction feel the same force in opposite directions. The bit that confused his colleagues, such they felt the need to clarify, is that all interactions are simultaneous. And as just a throwaway note that I'm not going to take anywhere, it's actually this fact that interactions have to be simultaneous that leads to the development of field theory. So in the next video, I'll talk briefly about the gravitational field, and in later courses, you'll learn about electric and magnetic fields. And it turns out this simultaneity issue leads to the development of that. But I'm not going to make a big deal about that here, other than just to say the two actions happen at the same time. So although we often talk about an action-reaction pair, that phrase action and reaction give a misleading impression that it's first one and then the other responds or something like that, and that is not the case. The interactions are simultaneous. And so I usually prefer using the phrase third law pair to reflect the simultaneity. And then finally, all interactions are of the same type. So as an example, the Earth is currently attracting you down, and at the same time, you are attracting the Earth up, both via the gravitational force. So it's happening at the same time. It's the same kind of force. It's gravity. The directions are opposite. The Earth is pulling you down, and you're pulling the Earth up, and it's mutual. There are two players involved, you and the Earth. Similarly, if you're sitting in a chair right now, there is a normal force of the chair pushing up to keep you from falling through the chair, but there's also a normal force from your butt pushing down on the chair. They are both normal forces, so it's the same type. The interactions are simultaneous. It's not one and then the other. Both your butt and the chair changed shape and are trying to push each other out of the way at the same time. The forces are in opposite directions. The chair is trying to push you up, and your butt is trying to push the chair down. And again, it's mutual. There are two players. And it's very important to recognize that with these third law pair forces, that there are always, the two forces will always be on different objects because of the fact that there are two players. So let's just take a quick exploration of these third law pairs. Or if you prefer, action-reaction pairs. So let's think about, say, you have your physics book lying on a table. Let's go ahead and start by drawing free body diagrams for the book and the table. So with the book, we can go ahead and actually, let me go ahead and cryptically copy and paste this so I don't have to redraw this figure again in a moment. There we go. So for the book, go ahead, draw a force identification diagram. The circle cuts through the table, so there is a normal force. And here I'm going to be very careful and say this is a normal force of the table acting on the book. And then we look for any long-range forces. And there's just the usual thing of gravity. And I am going to be very careful and say that this is from the Earth on the book, like so. All right, so now let's draw a free body diagram for the book. The book's just sitting there, so since the acceleration is 0 by Newton's second law of motion, this tells us that the normal force up, so this is the normal force from the table on the book, and the force of gravity down, since the net force is 0, these have to be equal and opposite. All right. So just as a quick pause and ponder here, so these happen to be equal. I want you to ask yourself, are these an action-reaction pair? The answer is no, they are not. They just happen to be equal and opposite, but they're not an action-reaction pair for several reasons. One, the two forces have to be on different objects. Both of these forces are on the same object, so it flunks the different object test. Secondly, the two forces have to be the same kind. Here we have gravity and normal. So they're two different kinds of forces, so it also flunks the same kind test. So this is an example of what I like to call a second law pair. Second law pairs are when you just happen to have the requirements of Newton's second law of motion, usually when something isn't accelerating, require that two forces just happen to cancel, and then they would be equal and opposite. I call that a second law pair, but this is not a third law pair. To try to suss out the third law pair, we're going to need to start drawing free body diagrams for the table, and then eventually even also the Earth. So let's do the table here. And I'll draw its free body diagram in blue, just so we can keep it straight. So again, same deal. So now here we do have to pay attention to the fact that the table is on the floor, is on the Earth. So now let's go ahead and do a force identification diagram for our table. So I need to draw a circle around the table, like so. And we can see here that it cuts through the book. So there's a normal force of the book on the table. There is also down here a normal force of the Earth on the table. Then finally we need to identify any long-range forces. We'll have a force of gravity of the Earth on the table. All right, actually let me drag that down a bit so we have a little more room, and even maybe over to the side a bit. There we go. So let's go ahead and draw our free body diagram. So first off, let's start with the lowest hanging fruit we got, which is a normal force of the book on the table. Now that might not seem like it is, but it is. And that is because this is a third law pair. This force and that force are a third law pair. Now, some authors will draw dotted lines between forces that are third law pairs. I like doing things like for the first third law pair I find, I will put a single slash through each of the force arrows involved. And then when I find my second one, I'll do 2 slashes and so forth. I find that just keeps the diagram a little cleaner. Okay. So then let's see here. What else do we have? Well, probably the next easiest one is going to be that there is a force of gravity from the Earth on the table pulling down. And I should really have these both attached to the same dot, but then it would make it cluttered. So kind of think of this as the same dot. And then finally, we will have a normal force of the Earth on the table pointing up. And this will equal the sum of these two, because again, since the acceleration is 0, the net force is 0, so that means the total forces up have to equal the total forces down. All right, now here there aren't any second law pairs, so we don't have to get all fussed about that. But I think it would be a good exercise for us to go and identify where the third law pairs are for all of these other forces. To do that, we need to draw still yet another free body, another picture. This time we are going to draw the Earth. Whoops. Black, please. Thank you. We're going to draw the Earth. And sitting on the Earth is our table and our book. Greatly exaggerated scale, but just roll with it here. So again, same deal. We'll draw a circle around the Earth and see what the circle cuts through. It cuts through the table. So there is a normal force of the table acting on the Earth. And then long-range forces. There are 2 forces of gravity. One is the table pulling up on the Earth. and the other is the book pulling up on the earth. Let's draw this free body diagram in purple. Sure, why not? So when we draw our free body diagram for the earth, what are we going to have? We are going to have, sorry, I somehow forgot to label normal force of book on table there. Okay. So we are going to have the normal force of the table on the earth. Oops, go back to purple here. There we go. And again, I'm picking that just because that's sort of a low-hanging fruit third law pair. A lot of times when you have forces that are hard to find, looking at the other players in the problem, it might be obvious, much more obvious, which way a force has to point on the other thing. And then you can use the fact that third law pairs always have to point in opposite directions to locate your object. So here, this and that are third law pairs. And then we had two forces of gravity. We will have the force of gravity of the table on the earth. That's a third law pair. Then usually once I've gone through 3 slashes, that's starting to get cluttered enough that I'll switch to drawing with X's. And again, I'm going to have to kind of fudge my dot over here, but let me draw in the force of gravity of the book on the earth. I'll put an X through it and up there. Those are also third law pairs. So normally you don't need to go that far. Most of the time you do not need to identify every possible third law pair in a problem. But I just wanted to take one all the way through just so that we could be particularly clear about that. All right, let's do one more. So this one here is, I'm just going to ask you to think about a tug-of-war. So we've got, oops, this is going to be pretty ugly here. So we've got one person here who's tugging onto the rope and they're happy because they're winning. Got another person here who's tugging on the rope and they are unhappy because they are losing. There we go. And they're particularly unhappy because they're about to get pulled into the river. Okay, so here's the issue. The force pulling on each of the players is the force of the rope, right? And that's set by how hard each of them is pulling on the rope. So if you think about it, that means that both players in the tug-of-war are literally pulling equally hard. So why is it that we ever have a winner in tug-of-war? And while we're at that, I will just also point out that while mass is correlated with who will win a tug-of-war, it is not always the most massive team that will win. All right. Well, this one turns out to be a bit of a mess. So let's start by drawing free body diagram for the winner here. So there is going to be a normal force exerted by the Earth on the winner. I'm just going to say NW. There's going to be a force of gravity exerted on the winner. I'll call that FGW. Those are a second law pair because the contestant is neither crashing through the surface of the Earth nor levitating off of it. We know that for the winner to be winning, they must be feeling a net force to the left. So while there's definitely a force due to tension of the rope pulling the winner to the right, something has to be pulling the winner to the left more than the rope is pulling the winner to the right. And that something is static friction. So there will be a force of static friction, and this is very much not to scale because that force of static friction should almost certainly be less than these, but just roll with it. Doesn't have to be. Maybe the guy's wearing cleats or something. I don't know. So there's a force of static friction of the Earth due to the Earth acting on the winner. And it is bigger than the force of static friction of the, it's bigger than the force of tension acting on the winner. And so the winner is feeling a net force to the left. We'll just make the rope massless here just to avoid some needless extra complication. So for the loser, there is also a force due to tension on the loser. Same rope, same force. It's an action-reaction pair. Alrighty. It must be the case that the net force on the loser is also to the left. So what's going on here? Well, we've got a normal force acting on the loser. We've got a force of gravity acting on the loser. Again, I've kind of got the scale drawn badly here, but sorry about that. Then we'll have a force of static friction of the Earth on the loser. So this force of static friction is less on the loser than it is on the winner. Now, this isn't coming from nothing. Let's draw a free body diagram for the Earth. And while there are a zillion forces acting on the Earth, we will just think about these two forces of static friction. So why was the Earth trying to push the winner to the left? That's because the winner, when the winner was extending their legs, their foot was trying to push the Earth to the right. So this is the winner on the Earth. Similarly, the loser, by extending their legs, is attempting to push the Earth to the left. And that is also a third law pair. Now, it turns out that the loser wasn't capable of extending their legs as well as the winner. And so the winner is actually doing a better job of pushing the Earth to the right than the loser is pushing the Earth to the left. Now, you might ask, hey, this seems ridiculous. I don't think the Earth is moving at all. And the answer to that is you're incorrect. The force is unbalanced on the Earth here. But remember, Newton's second law says that the acceleration of something, in this case the Earth, will be the net force. Okay, maybe 1,000 newtons, maybe, on that order, over the mass. Well, for crying out loud, that's the mass of the Earth, which is an absolutely absurd number. So it turns out that the winner does is actually pushing the Earth to the right harder than the Earth is pushing, the loser's pushing the Earth to the left. The winner does succeed in pushing the Earth to the right, and the Earth is indeed picking up speed to the right. However, that acceleration is so small, you will never, ever notice. All right, in the last video on this series, I'm going to take a look briefly at gravity and weight. Catch you on the flip side.